Okay, so in this video we're going to have a look at some difficult vector proofs where we don't have any diagrams, and we're going to build up to the kind of question that you can see on the screen. Now it would be good if you did have a good understanding already of vectors, so I will link any lessons in the description that I think you'll find helpful for this topic, but we should be able to just go through this without necessarily having a huge understanding of vectors already. But with that being said, let's get started. Okay, so we're going to start by having a look at this question. It says that A, B and C are 3 points such that A to B is 3A plus 4B and A to C is 12A plus 16B. Prove that A, B and C lie on a straight line. Now if they did lie on a straight line, which is what we're going to prove, if we imagine what this might look like, we might have A at the end, B somewhere over here, not necessarily in the middle, and C, let's just put it at the end of this line. Now if we think about vectors and what A and B means, A and B, if we just had A plus B, maybe A moves us to here and B moves us, let's say, to there. So let's just imagine that's A and this is B. Now when it comes to vectors, we can do any multiple of that vector as long as we keep the amount of A's and B's the same. So for example, if we did 2 A's from the same point, that might take us over to here. I'm trying to draw double the distance there. And then maybe 2 B's would take us over to here. And that'd land still on the same straight line. I'm just going to put I'll put 2A there for the purple line. So as long as they're in the same multiple, or in other words, maybe they share the same scale factor, then they will be on the same straight line. And that's what we're going to try and show using a bit of algebra. Of course, if they weren't in the same multiple, then they wouldn't necessarily land on the same straight line. Because if I did 2 A's and then maybe I only did 1 B, well, I'd only land around about here. Or maybe I'd do 3 B's and that would land somewhere over there. If I did something like 3B, they would no longer be in the same multiple. I've doubled the amount of A's and got to 2A, but I've tripled the amount of B's, and therefore it's not going to land on that same straight line. So how do we actually go about showing this, particularly when we don't have a diagram? Well, the fact that we don't have a diagram means I think it actually helps just to draw a little diagram just to help to visualise this. So I've drawn this straight line. Now it says that A to B is the vector 3A plus 4B. So whatever direction that goes in, this vector here that takes us from the A to B is 3A plus 4B. And it says that the full line from A to C, and so I don't have to draw over the top, I'm going to draw another one in here. So the full length there is 12A plus 16B. Now because that's the larger line, that means I've probably multiplied this smaller one by something in order to get there. Now we want to show this and prove it, and to stick with the same method that you use for some of the harder vector proofs, I'm actually going to follow the same method. So I take the larger vector, that 12A plus 16B, I'm going to factorise it and see what I get on the outside. So if I do factorise that, 12A and 16B, let's just write that down here, 12A plus 16B, well, they both divide by 4. So I could write that as 4 on the outside of the bracket. On the inside of the bracket, we'd have 3A's plus, and what do we times 4 by to get 16? We'd get 4B's. Now straight away, as soon as you've written that line, you should be looking and thinking, fantastic, I've definitely got this now, because that bracket there matches that smaller vector. What that means is it's going in the same direction. If you remember, I drew those A's and B's, as long as I did the same amount of A's and B's, it was definitely going in the same direction. So this new vector, or this larger vector, is definitely going in the same direction, but it is going 4 times sort of more in terms of its distance. So it's 4 times the size in terms of its length. So if I wanted to kind of redraw that diagram, I'd probably put the B a lot closer to the A, so my diagram isn't accurate, but I've shown, or I've proved that they're definitely on the same straight line. So you could write some words with this if you wanted to add some more information. I could write they share the same vector, but 4 is a multiple of the vector AB. Okay, and you could write some words along with that as well, just to sort of back up your proof to show that you know what you're on about. You haven't just factorised it and you think you've got the right answer. Okay, so I might just write something, point a little arrow to the 4, and just say it is a multiple of the vector a to b. Right, there we go. Let's have a look at another question, very similar to this, but with some slightly harder factorising. Okay, so a very similar question. A, B and C are 3 points, such that A to B is 5A minus 3B and A to C. You can see here why it's more difficult. We've got 12.5A minus 7.5B. Prove that A, B and C lie on a straight line. Now again, if I draw my line, and again I'm not going to draw it accurately, I'm just going to draw a straight line just to help me visualise it. And to be fair, once you've got the hang of this, you probably don't need to draw the line, but it does help just to get a bit of a visualisation. And mainly because I just want to make sure that I'm doing the right thing. So it says A to B is 5A minus 3B, and then I'm always just double checking because it says A to C, which is the full length of the line, and that's 12.5A minus 7.5B. And obviously it's quite easy to look at the numbers and see which is the bigger vector, but if I'm getting used to sort of labelling on the diagram, it's just going to help out with obviously harder vector proofs as well. So looking at this one, so I want to take that larger vector, which is my 12a minus the 12.5a minus the 7.5b, and again I want to think, what does that actually factorise by? Now you might have done some vector proofs before and you'll know that you can factorise out fractions or decimals. And if this has a 0.5 in there, the chances are it's going to be one of either 1.5, 2.5, or possibly even 3.5. Again, it could be any of these variations. It might even be a quarter that comes out. But these are the ones that I'd look at first, just to think, well, do they divide by any of these nice, easy decimals? I don't want to say easy because factorising by one of those isn't easy, but let's just have a look. Now looking at 12.5 and 7.5, I already know that they divide by the 2.5. So I know I can bring 2.5 outside the bracket. And I'm just going to hope that when I take 2.5 out the bracket, that it does in fact match this 5a minus 3b that we have in our smaller vector. So if we put 2.5 on the outside, we're going to get, how many times does that go into 12.5? Well, if you count up in 2.5s, 2.55, 7.5, 10, 12.5, and we get that 5a, and straight away we've got the match with the 5a up there, so that's a good thing. 7.5, that's 2.55 and then 7.5, so that's 3, so that is minus the 3b. There we go, we've got a match in terms of our direction, but this vector here is 2.5 times bigger than that smaller line a to b. So our full line is 2.5 times the size of that. So there we go, that's how we go about proving these without a diagram. I've got a couple of questions for you to have a go at, and then we're going to have a look at those trickier questions that I showed you at the start. Okay, so there's 2 questions here. I want you to pause the video, have a go at these 2. We'll go over the answers in just a sec. Okay, so looking at the first one. Now our larger vector, I'm not going to draw the diagrams for these just to be a bit of time saving here. They both divide by 3. So if I put 3 on the outside, that would be 6a minus 5b. On the inside of the bracket, it's a multiple of 3. So again, I would say it's 3 times the size of the vector a to b. A mathematical way that you could write that, you could write something like this. A to c is equal to 3 lots of a to b. And that'd be a really good way of writing that without having to write loads of words. You're just saying there that a to c is 3 times a to b. Have a look at the next one then. Again, we have decimals. So in my head, again, I'm just thinking 1.5, 2.5, 3.5 to try those, as we have some 0.5s there. It doesn't look like they divide by the 2.5, as we've got a 4.5 there. So instead, I'm just going to try the 1.5. I know that 1.5 goes into 4.5 because that'll go in 3 times, which is perfect because that matches the 3. And 1.5 times 10 is 15, so perfect. 1.5 on the outside, and on the inside we'll have 3a plus the 10b, and then again we've got our matching vector 3a plus 10b, but this one is 1.5 times the size. So again I could write the vector a to c with our arrow above it is 1.5 multiplied by the vector a to b, or 1.5 ab. And there we go, we've proved that. So this was all just about factorising and just understanding what that means when we factorised it. Why does that show that it's on the straight line? Okay, so looking at a slightly harder question. Now this is quite a big step up from the last one, just in terms of the way that you visualise it and actually break down this problem. In terms of the maths behind it, it's no harder than what we've just done, other than the fact we have a final step here, whereas it wants us to write the ratio of the lengths. But if you're okay at writing ratios, that's not an awful step. So it says D, E and F are 3 points on a straight line, such that D to E is 5E plus 8F, but E to F is negative 17.5E minus 28F. Find the ratio of, and then we've got the ratio D to F and D to E. Now if we sort of visualise this, and again if I put it as a straight line, let's just think about what this means in terms of the 3 points. Well, if this was D, and let's say this was E, well, we know that that vector goes from D to E, and that's absolutely fine. But it tells us that E to F is a negative amount of E and F, and a negative amount of both of them means it's going in the other way. So if I was to go backwards, and it's obviously bigger numbers, it's going to go way back here. So F would actually be over there. So when I draw my line, I just want to think about that in terms of what it's going to look like, because maybe putting D, E and F in the order that it's given us in the question isn't going to suit this particular example. So if we say that this is D and this is E, and that's fine because that vector there would be 5E plus 8F, and then the vector going from E down to F is going backwards, well then this one over here must be the F. And we can kind of draw that above like I did on the last example and just put the direction going that way, because that's negative 17.5E minus 28F. Now to be fair, at this point, what do we actually want to know? Well, we want to know the gap in between, because it wants us to write the ratio D to F, which is that first portion of the line, this one just here, and it wants us to write the ratio D to E. We've got the size of that line, we've got the 5E plus 8F. We'll think about the ratio when we get there. But let's think about the gap that's actually missing. Now if we look at these numbers, it doesn't really matter that these are negative. Yes, it's going in the opposite direction, but let's just think about the size of the numbers. There's 17.5 E's, and this part here we've only got 5 E's. So it doesn't really matter what direction I draw this part of the line. If I draw it in this direction, I can write them as positive. If I want to put them in the other direction, which I can, I'd just write them as negative. But it doesn't really matter. So I'm just going to put them going the same way, just to avoid writing the negatives. But if the gap, the full length of the line is 17.5, then this must be 12.5 E's, and there we go, in order to balance that out with the 5 E's, and then they all balance out to 17.5. I must also have an amount of F's. Now over there we have 8 F's, and the full length is 28 F's, so that must be a gap of 20 F's. Now that all balances with the other few. Yes, I've moved it into a positive direction, but of course I could write it the other way. I could have written minus 12.5E and minus 20F. Okay, which is a little bit strange, because if you think about adding them together, that would be a little bit odd if I wrote it the other way around, because it wouldn't actually equal negative 17.5, but that's not really what it's saying. It's saying it's just going back that amount of 17.5s. So we want to write them in the same order really, so that we get a full sort of example of the line, because if we were to add those together now that they're in the same direction, they do equal 17.5E plus 20F, and if we were to do that backwards, it would match our negative 17.5E minus 28F. There we go, make sure that's an 8, not a 0. So there we go, our line balances, we've got the right amount, now we just need to think about the ratio. To get the ratio, we're just going to do what we did in the first part of this video. We're going to factorise the larger part of this vector here and just see what we get. Hopefully we get a match on that 5e plus 8f, otherwise it's not on the same straight line. So 12.5 and 20, well again, I'm looking at my 1.5, 2.5s and 3.5s, and they do divide by 2.5. So if I factorise by 2.5, that would be 5 e's and thankfully 8 f's. So there we go, it does balance. So although we're not going to factorise the first one because we've got a match in terms of our 5e add 8f, it matches on both. But in terms of the first vector, d to e, that's one lot of 5e plus 8f. And for f to d, this one we've just done, that's 2.5 lots. So for d to f, the one we've just done, or f to d in terms of the way we've drawn it, that would be 2.5. Okay, there we go. Not 2 dots, just the 1 dot, 2.5, and the other one is just one lot of that, so 2.5 to 1. Now, of course, that's not normally how we'd write a ratio. We want to make sure it's whole numbers. As it's got a 0.5, we could just times them both by 2, and that would be 5 to 2, making sure we multiply both sides of the ratio. So there we go, our ratio of those side lengths is 5 to 2, and there we go, that would be our final answer. Okay, so a relatively tricky question. Not too bad once you start to draw it and you realise what this minus part actually means, and it doesn't really matter that it's negative, it's just that it's going in a different direction, and that we're really just looking at the size of the different letters. So in this case it's E's and F's, so we're looking at the size of the E, the size of the F, and just making sure that we balance that with that missing part of the line. So there we go, I've got a question for you to have a go at, so let's have a look at that one now. Okay, so here's your question, very similar to the one that we've just done. Once you've done this one, I've got one final question for you to have a practice on as well, because these are relatively tricky. You probably want to do more than one, but pause the video there, have a go at this one. We'll go over the answer in just a sec. Okay, so looking at this one then. So d to e is 7e plus 6f, and then e to f going backwards is that full length. So d to e takes us from here to here, and again I do think it does help to draw these diagrams. E to f is going backwards, back through D, all the way down to F, and that's down here. So the D to E part, this one here, we have 7e plus 6f. The full length of the line, which I'll draw just over the top again, is negative 17.5e minus 15f. And there we go. So we've got 17.5 for the E, 15s for the F. So for the E at the moment, we've got 7 E's there. So we're going to want, and again I'll put it in the same direction, it doesn't matter if you did it the other way, I want another 10.5 E's, so 10.5 E. And we want to get to 15F. At the moment we've got 6 F's, we want to get to 15, so that's going to be another 9, so plus 9F. And there we go, we've got both of our vectors. Again, this is the larger one, so 10.5 and 9, and we want to actually factorise. So thinking about what numbers go into that, and again it's got a 0.5, so let's go with the 1.5, 2.5, 3.5. I know it's not 2.5, so I'm going to cross that one out. I can just see it because it's going to go 10 and then 12.5 if it was 2.5s. So hopefully it's the 1.5. So if we count up in some 1.5s, you've got 1.5, 3, 4.5, 6, 7.5, 9, 10.5, that's 7 times. So hopefully it goes into 9 as well. In fact, I did say 9 then actually. So 1.5 brackets, that was 7e, and it was one before that that hit the 9. So 6f's, so 7e plus 6f's. Perfect. And that matches that same vector, 7e and 6f. So there we go. We know we're pretty much done. We just have to write that ratio. So it's the ratio d to f first. D to f, we've got 1.5 lots of that vector movement there, and d to e was just one lot of that vector movement, so that's 1.5 to 1. Again, a nice easy movement to make these whole numbers, times them by 2, and that would be 3 and 2, and that would be our final ratio there, 3 to 2, and there we go, that's our final answer. Cool. Right, as I said, we've got one more of these to have a go at. It's pretty much the same, so it's just another practice question, but let's have a look at that one, and that'll be our final question on this video. Okay, so here you go, final question. Hopefully you get this one right. So pause the video, have a go, we'll go over the answer in just a sec. Right, okay, so speeding things up, drawing the line. Let's just draw this in. Normally when I say speed things up, I make a mistake, so I probably shouldn't do that. Let's just slow it down. D to E, and then also E to F going backwards. Cool, happy with that. D to E is 5E plus 4F. Going backwards, the full length of the line, that is negative 17.5E minus 14F. So the gap, looking at that, we've got 17.5e and 14f. So we want to get another 12.5e here to make that balance. We've already got 4f's, we want 14, so that'd have to be plus 10f. There we go. Now we're just going to have a look at a comparison and do our factorising and hope we get that 5e plus 4f. So again, 1.5, 2.5 and 3.5. Looks like this time it's going to be that 2.5 again. Didn't get any 3.5s. So 2.5 on the outside. That's going to be 5 times to hit 12.5, 4 times to hit 10, so 4f. And there we go. We've got our matching bracket there. So it's definitely going in the same direction. So finding the ratio d to f and d to e. D to f is 2.5. D to e is 1, and there we go again. We just want to make those whole numbers, so 5 and 2, and there we go. Happy with that. Our ratio is 5 to 2, and there we go. And that is how you would approach vector problems without a diagram. Now, of course, questions like this, any kind of question could come up. These were all very sort of similar in the way that I arranged them, obviously, so to make sure you got some good practice. So I'll have a look at making a few more videos similar to this, but hopefully this will give you a really good understanding of just how you would go about approaching these questions and the importance of drawing a diagram and really thinking through the problem before you just go straight in and start trying to tackle it. But there we go, definitely something very different to my normal or my other vector videos. But as I said, they are all in the description, so make sure you go and check those out as well, because they all link together and all of them will help you have a better understanding of vector proofs in general. There we go, I hope you enjoyed the video. If you did, don't forget to like, don't forget to comment, don't forget to subscribe, and I'll see you for the next one.